So we're back with our last example. And this one is actually a model of population growth. And so what I want to share with you is that really exponential growth means growth without any restraint, ever. So think about, does anything really grow without any kind of limiting factor? I have fish in my pond. I have 10 fish. I have 100 fish. Can I have 1,000,000 fish? Can I have 10 trillion fish in a pond that's a half acre? No, I can't. So at some point, you're going to have limiting factors. You're going to have space. You're going to have resources like food and oxygen. You're going to have things like predators. So at some point, populations stop growing. We've looked at something else like that about a month ago, the whole phrase of flattening the curve. Well, a true flattened curve is one that is a logistic curve. And it starts out looking like an exponential, but then it flattens off because it has some kind of limiting factor that instead of just growing and growing unrestrained, that at some point it flattens out and approaches some number. The dogs are barking. So this is what a logistic growth equation looks like. And when you look at that, you're like, oh my stars, it's all letters. Where did the numbers go? I know, okay? But I'm going to tell you who everybody is. F of t, okay, so that's the amount after time t, equals C. C is the max value that you can have, all right? Divided by 1 plus a times e to the negative bt. So you see it's still exponential, but it's exponential in the denominator. So it does something to the curve, right? Then over here I've told you a, b, and c are positive constants. B, which is in the exponent spot, is a number between 0 and 1. Okay. So what I want to do is show you what this curve looks like. So I'm going to jump over here to Desmos, and I've actually put in Desmos the equation that we're going to use. I'm going to do a population of fish in my pond problem. For all you wildlife biologists or marine biologists, you'll be doing stuff like this, okay? Here's this equation. And so this is my C value, 1880. And then I have what? 1 plus 1.42 times e to the negative 0.037 t. So there's my equation. And I've typed it into Desmos, and I'm over here looking at the graph, and I'm going, I don't see it. What's wrong with this graph? What's wrong with this computer? What's wrong with this calculator? Nothing. I'm looking at the wrong window. So remember we said C was the max Y value. Look up here, 1880. Look at my Y value, 40. I'm not going to see it. So I got to zoom out. Fortunately, on Desmos, that's pretty easy. It's just, oh, look, it's starting to show up. Okay, so far it looks like an exponential, doesn't it? Looks like an exponential. Cosgrove, I thought you said this wasn't an exponential. Looks like one. Look, it's rising rapidly. I mean, it's shooting up. It's still growing. It's still growing. Oh, uh-oh. What happened? Look at there. It's like nothing, 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 nothing. Whoosh! And then shh, completely flattens out. And guess what it's approaching? It's approaching, you see that value, 1879.991? It's approaching the horizontal constant of 1880 because that's the number that's in the numerator. Pretty cool. This is a logistic curve. Now, if you zoom out far enough, it sort of looks like a cubic. Sort of. Not really, not a cubic, cube root, sorry. Sort of looks like a cube root-ish. Okay, that's probably the closest thing I would say that we've done that it looks like. So you have this initial nothing, and then you have this extremely rapid expansion of just phenomenal growth in a very short amount of time. And then what? Flattens out, okay? It doesn't grow anymore. When you're in calculus, you will learn that there's a point right in here where it starts, instead of increasing at an increasing rate, it starts to increase at a decreasing rate. It starts to slow down, all right? That's called the inflection point. When you're in calculus, you learn some cool stuff about second derivatives and inflection point, but that can wait a couple of years. We are going to look at a problem involving fish in a pond and actually this equation, okay? So here's our graph. So we're going to come back to this graph, but let's go and look at the problem, okay? This is what we know so far, okay? And then here we are. We know that there is, for specifically, we have a population of fish in a pond. And we have the equation that it's modeled by. So we'll say P of T, so the population over time, is equal to 1880, that's our C, divided by 1 plus 1.42 times e to the negative 0.037 t. And this is just an equation that models the population of fish, right? So the first thing they're going to ask us to do is look at the graph. Okay, so if I come over here, okay, so part 1 is look at graph. Okay, so let's look at it. Let's come back over here. There we are. It's interesting, right? So it's going to ask us, all right, it seems to start out as exponential, but then it flattens out. So what is this number that it seems to flatten out? So if we look, let me come back over here. This is 1500, 16, 17, 18, 19. This is 1900. So somewhere, that's 1900. That's what? 20, 40, 60, 80. So it seems to flatten out at 1880. And you know what? It does. And we could have predicted that based on the equation. So let's come over here because it's going to ask us about the graph, right? What does it seem to approach, right? So we're going to say the y values approach, which means they get near but never touch 1880. 1880 fish. Okay? The second question is going to ask us about the horizontal asymptote. Well, it's really the same question as the first one, but that's all right. Where is the horizontal asymptote? Well, that's this C value right here. And what is that? 1880, all right? So it is y equals 1880. All right. Then it's going to say, what's the max population of fish? Guess what? C is what? The max y value that the curve approaches, 1880. So in this particular example, it asked the same question 3 different ways. And it did that for you to make a connection between the max y value, the horizontal asymptote, and actually in the question, connect it with the max population. All right. But what we need to do is it's going to ask us this. When will the population reach 1,875 fish? And this is the kind of thing actually that, say, marine biologists or wildlife biologists would use this particular problem for because they have to do a lot of predictions based on models to determine are the constraints or restrictions that they're using being helpful. If you've ever been fishing, they put limitations on fishing. You can only catch 2 red snapper, and it's only from this time to this time. Or you have a slot limit. You can only catch, if you catch ones that are this size, you have to put them back. If you catch ones that are this size, and so all those restrictions help preserve the population of fish for it to grow. When will the population reach 1875? All right, so this is my amount after time t. When, that's an unknown thing. I don't know, that's the time. So they're asking me, what's t? Okay. So if you look in this equation, p of t is 1875. The only other variable is right here. So I'm going to work backwards and find him. Okay. All right, I'm going to need a fresh page, so I will go ahead and get a fresh page, and we'll say 1875 is equal to 1880, that's the numerator, divided by 1 plus 1.42 times e to the negative 0.037 t. And there's my variable. And my variable's in the exponent spot, so that means at some point I'm gonna have to do a log to get the variable out of the exponent. So we can't logify yet because we got all kinds of crap going on over here, not just an exponent. So let's get this guy out of the denominator. And how do we do that? Well, we multiply both sides by this, and then we'll divide by 1875, right? Cross multiply, however you want to think about it. But we end up with this. How do we clear the denominators? Is multiply by what's in the denominator. So we're going to have 1 plus 1.42 e to the negative 0.037 t, right? Which is going to equal 1880 divided by 1875. Okay. Because really, what's over here? This, remember, is really over 1, right? So we multiply these two, multiply those, or you can just say what? Multiply both sides by the denominator. Then to isolate t, we're going to divide both sides by 1875. And there we go. Okay. That's not really algebra. That's pre-algebra, but just manipulating proportions. So now here's our t. Again, we know we're going to have to take a log, but not yet, because e isn't isolated. So look, we're adding 1, and then we're also multiplying. So let's get rid of that 1 first by subtracting. So 1.42, oh my stars. 1.42 e to the negative 0.037 t is equal to 1880 divided by 1875 minus 1. And we'll simplify that in a minute. Don't worry about it. Now what? Now let's divide by 1.42. Okay? And we get e to the negative 0.037 t equals, now we can get our calculator, but just be careful. So we're going to say 1880 divided by 1875, and we get a hair more than 1, okay? And now I'm going to subtract the 1, and we get a hair. And now I'm going to divide that by 1.42. So it's going to be a small number. So divided by 1.42. All right, tiny, 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 okay? So now I'm going to say, I really don't want to round here, okay? My calculator has it stored, but I'm going to go ahead and write it out. 0.0018779343. So if at all possible, don't round. The only time we're going to round is at the very end, no intermediate rounding. So you notice what we have, e to the stuff equals number. Okay. And now I can put it in log form to get the t out of the exponent spot. So I'm going to say the natural log of, guess what? All of this, okay? So just as a shortcut, I'm just going to do this, okay? The natural log of 0.0018779, but don't round, okay? No rounding, is equal to negative 0.037t. And then the last step is to divide by negative 0.037. And we should get a value for t, and it's going to be approximate, okay? So here's the deal. You're like, well, now, wait a minute. How can I use that answer over there without recopying it or copying it down wrong? I don't want to do that. So that's my answer. You can tell your calculator to use that, okay? So I'm going to say the natural log of, and now I'm going to push the second button and then the minus button. So see, right above the minus in blue is the word ANS. So look at there. That's shortcut. Some of you know that. I don't know if everybody does. Second answer, all right? So I'm going to take the natural log of that big number and then hit enter, and then divide it by negative 0.037. See that? 169.664. That is the time in years that it's going to take for the fish population to reach 1875, right? So I have 169.6. Oh, that's a pitiful 6. 6, that looks like an E, sorry. 6,644. So we'll say it will take about 169.66. Okay, that's 2/3. 2/3 of a year is 8 months. Or 170 years for fish population to reach 1875. All right, and that is using the logistic curve to help you figure out populations. So all you wildlife biologists, all of you marine biologists, all those of you that want to work with animals in a really cool way, even if it's just in vet medicine, which is huge, so I didn't mean to say even if, but anyway, that is a logistic curve, which is appropriate in so many applications, and you heard it first right here.